Okay, so here's theorem 1. It says any matrix represents a homomorphism between vector spaces of appropriate dimensions with respect to any pair of bases. So the proof is pretty straightforward. So let's just go through it here quickly. It says we must check that for any matrix H and any domain and codomain bases B and D, the defined map H is linear. So if we take V and U, vectors V and U in the vector space V are such that the representative with respect to B of V is equal to this column vector V1 through Vn, and the representative with respect to B of U, the vector U, is given by this column vector of U1 through U sub n, okay? And C and D are in the reals. The calculation of H, taking H, the mapping of the linear combination of V and U, CV plus DU, can be broken down in this regard because we're going to take C times the linear combination of V1 times the basis, right? And so we're going to get, when it's all said and done, and again we're doing the representation towards the H matrix, so again we have some H matrix, so it's going to H11 times the linear combination of C1 plus D of U1, right? All the way through H1n of CVn plus DVn, so that, and then that linear combination is going to be multiplied by delta 1, right? So that's the basis vector for the codomain basis. And then we're going to plus all the way through, and then we're going to go finally the final what is it? The final, is it the row? I think it's the row. So HM1 times, again, this linear combination, plus all the way to HMN times this linear combination times the final basis vector, right? Because all we're doing is we're doing the matrix multiplication here. And then finally, when we get all said and done, what do we end up with? We end up with C times H of vector V plus D times H of vector U, which supplies the check that we needed to do. And hence it's linear. And we're done.